We've been talking about Lewis theory and electron geometry. Lewis theory is a very good starting place, but it doesn't have the qualities to be a robust prediction. So while it can predict trends, it doesn't give good numerical predictions. So there's no way to get a number for bond strength or bond length from Lewis theory. It will give a good first approximation of the bond angle, but if you want to find the actual angle, Lewis theory is not where you're going to turn. It can't write one correct structure for molecules where resonance is important. You have to draw two structures or more. And it doesn't always predict the correct magnetic behavior. So for example, oxygen is paramagnetic, but Lewis structure would predict it to be diamagnetic. So we are going to move on to our next theory of bonding, and that involves orbital interaction. So as two atoms approach each other, the half-filled atomic orbitals on each atom are going to interact with each other to form molecular orbitals. And then these molecular orbitals are more stable than the separate atomic orbitals because they're going to contain paired electrons shared by both atoms. So let's take a look at what unhybridized carbon orbitals would predict. So remember, carbon, with its 4 valence electrons, has 2 electrons in the 2s and 2 in the 2p. If you neglect Lewis theory and just think about interacting half-filled orbitals, you would predict that 2 hydrogens would bond with these half-filled orbitals, and you would get a 90-degree separation from the p orbitals, and that's not what happens. We see 4 hydrogens bonding with the bond angle of 109.5 degrees as predicted by Lewis theory. So to explain this, how orbitals interact, we're going to talk about valence bond theory. So partially filled or empty atomic orbitals don't predict the number of bonds or the orientation of them. So to adjust for that, we're going to hybridize these orbitals together into molecular orbitals and then form the bonds. So if we're talking about our carbon from the last slide, we're going to mix the 2s and the 2p orbitals. So there's 1 2s orbital, 3 2p orbitals. So add those 4 together, mix them up, and we're going to get 4 equal orbitals that are going to point at the corners of a tetrahedron. So the concepts here for valence bond theory: the valence electrons reside in their quantum mechanical atomic orbitals that we've talked about. They can be the s, p, d, and f orbitals, or we can mix those together to form hybrids. A chemical bond is going to result when those atomic orbitals interact to get 2 electrons in this new molecular orbital. And the shape is going to be determined by the geometry of the interacting orbitals. To make these hybrid orbitals, all we're going to do is add together how many standard atomic orbitals we're mixing together, and that gets us the number of hybrid orbitals formed. For instance, if we combine a 2s orbital with a 2p orbital, 1 orbital plus 1 orbital gets us 2 2sp hybridized orbitals. So the way we name our hybrids is we keep the number out front of the principal quantum level, and then we put the orbitals that we've hybridized next to each other. So a 2s plus a 2p is going to be 2sp orbitals, and there are 2 of them. Hydrogen doesn't hybridize because it only has the 1 orbital, the 1s. And then the number and type of those atomic orbitals is going to give us the shape. Let's look at an example. carbon has three ways that it can hybridize. So unhybridized, remember, as 2 electrons in the 2s and then 2 in 2p orbitals. If we do a sp hybridization, we're taking our 2s orbital, we're adding in one 2p orbital. That gets us 2 equal orbitals that are called 2 sp orbitals. Then we still have these other unhybridized p orbitals that still have 1 electron in them. So when we hybridize, we use the empty orbitals first and then any half full orbitals. And we go in order of energy, so the 2s always hybridize first. Then there's sp2 hybridization, where we're taking our s orbital plus 2p orbitals gets us the sp2, and then we can mix together all 4 of the orbitals, 1s plus 3p orbitals, to get us our sp3 hybrid orbitals. And then over here on the right, you can see a molecule that would have these hybridizations. For instance, hydrogen cyanide here has the carbon triple bonded to a nitrogen and bonded to a hydrogen. So we have our bond to a hydrogen is via an sp orbital. One of the bonds to a nitrogen is via an sp. The other 2 are via p orbitals. Our carbon here, our bonds to hydrogen are via sp2, and then our double bond, one of them is an sp2 and one of them is just a p orbital. And then our methane here, these are all sp3 hybrid orbitals that carbon is using to bond to the hydrogens. If you want to draw an orbital diagram for an sp3 hybridized orbital, you make your sp3 hybrids. Lone pairs generally occupy hybrid orbitals. So on our nitrogen here, if we're bonding carbon and nitrogen together, when we write our orbital diagram for nitrogen, the lone pair goes into a hybrid, and then we have 3 sp3 orbitals available for bonding. Our carbon here, we've talked about already. So let's practice drawing that. Draw the orbital diagram for the sp3 hybridization of each atom. So for chlorine, again, we're sp3 hybridizing, so we have 4 equal in energy orbitals. They are called 3 sp3 because we put that primary quantum number out front. And then we have 7 electrons to fill in. So 1, 2, 3, 4, 5, 6, 7 electrons. Our oxygen here, again, we're forming 4 orbitals. These are called 2 sp3. Again, the quantum number goes out front. And we have 6 electrons, and lone pairs go in hybrid orbitals. So it's going to look like that. Now, bonding is going to take place when atomic or hybrid orbitals interact or overlap. To overlap, they need to be aligned along the axis between the atoms, or in the case of p orbitals, they can be parallel to each other and perpendicular to the interatomic axis. We'll look at a picture in a minute. The bond with the overlap is called a sigma bond, and those can either be, so you're going to get direct overlap, and it doesn't matter if it's, s to s orbital, p to p, hybrid to hybrid, s to hybrid. It doesn't matter what type, as long as they physically overlap. A pi bond is when they're parallel to each other and perpendicular to the axis, and that only happens between unhybridized parallel p orbitals. So to get a pi bond, you need a p orbital. Now, this should be pretty straightforward that the interaction between parallel orbitals is not as strong as that between orbitals that are pointing at each other and overlapping. So sigma bonds are stronger than pi bonds. Let's look at what it's actually looking like. So if the bonds directly overlap, you get a sigma bond. If they're parallel to each other, you get an area of probability above and below the axis where the nuclei are that is probable for finding the electron. So that is a pi bond. If we draw an orbital diagram, overlap is going to be a sigma bond. Overlap between unhybridized p orbitals results in a pi bond. So we get something that looks like this. Our carbon here is tetrahedral geometry. You can also memorize, if you would like. Tetrahedral is going to be sp3. Trigonal planar is sp2. Linear is sp hybridized. So our carbon here forms 4 bonds. It is sp3 hybridized, and those all form sigma bonds with our hydrogens. Our nitrogen here is also sp3 hybridized, so it's forming 3 bonds and then has that lone pair that also goes into a hybrid orbital. And again, all sigma bonds are formed. For something with a double bond, we're going to end up with our trigonal planar geometry and a sp2 hybrid. So you can see our carbon here is trigonal planar, sp2 hybridized. So we have 1 electron in a p orbital and then 3 in 3 sp2 hybridized carbons. So we get sigma bonds with our carbons. We get a sigma bond between our oxygen and our carbon. And then our lone pairs for our oxygen are in hybrid orbitals. But then our oxygen and our carbon have p orbitals as well that are half full. So those are going to overlap and form a pi bond. So when you have a double bond, it's always 1 sigma bond and 1 pi bond. So an sp2 hybrid is always going to be trigonal planar. For carbon, it's actually trigonal planar. For nitrogen, it's going to be trigonal bent. For oxygen, it's going to look linear because it's not going to bond to anything else. You're going to have the 120 degree bond angles and it will be flat. Hybrid orbitals are for sigma bonds and lone pairs. Non-hybridized p is for the pi bond. So let's practice. Draw the orbital diagram for the sp2 hybridization of each atom. And then how many sigma and pi bonds would you expect each to form? So our unhybridized atom there, if we hybridize it, so this is sp2, 1s plus 2p orbitals gets me 3 of those. And then, actually let me draw this a little higher in energy. Up here, sorry, that's 2sp2, we get 1 2p orbital. Then we can fill it in. We get 3 electrons in our sp2 orbitals. Our 2p is empty. So I would expect this to form 3 sigma bonds and no pi bonds because that one is empty. Then here, same concept. We have our 2 sp2 hybrids and then a 2p orbital there. We're going to fill this in. How many like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I would expect this to form 1 sigma bond and 1 pi bond because I put my lone pairs in my hybrid orbitals. Then I have one unpaired here and one unpaired up in my 2p. So I'm forming one sigma and one pi bond. And this explains why boron is an exception to our octet rule. It's because of this sp2 hybrid atom that gives 3 sigma bonds, and then our 2p is empty. Let's talk about bond rotation. Because our sigmas are along the axis, we can rotate freely around that bond. But once we have pi bonds above and below, that rotation can't happen, because if you rotate, you break the pi bond. So for example, we have 1,2-dichloroethane here. There's free rotation around this single bond. But with a double bond, so 1,2-dichloroethene, we are limited. We can't rotate around that double bond anymore. So this leads to 2 possibilities for this molecule. We can either have the chlorines on the same side, or we can have them on opposite sides. And these 2 molecules are not equal to each other. They are isomers of each other. So here's that example. We have, this is the cis isomer, this one is the trans isomer. So cis means same side, trans means opposite. So those 2 molecules are not the same. All right, finally our sp hybrid. It's going to have 2 electron groups, a linear shape, 180-degree bond angle, and we're going to have 1 sigma bond and 2 pi bonds, because we're using 2 non-hybridized p orbitals. So 1 s orbital, 1 p orbital form this hybrid, and which you can see leads to the 180-degree bond angle. And then we have p orbitals going like this, and then coming out and going behind to form the triple bond. So for carbon, we're going to see this where we can form the sigma bonds with our SPs, and then the pi bonds with these half-filled p orbitals. Nitrogen here has a lone pair, can form 1 sigma and then 2 pi bonds. Here's a table from your book, table 10.3, that shows you the electron geometry and then that hybridization scheme and how they go together. And you can check out the 5 and 6 options as well. You can start mixing d orbitals in as well. So if we want to predict hybridization along with the bonding scheme, start with the Lewis structure, predict the electron group geometry, and then use the hybridization, sketch the molecule, label the bonds as sigma or pi. Let's go back to our boric acid, which we've looked at before. So I will draw it in a way that indicates the angles, except for this hydrogen here, which should be down a little bit farther because it's not linear. Oop. There we go. So our boron is trigonal planar, which means it is sp2 hybridized, and our oxygens are tetrahedral bent, which means it is sp3 hybridized. One more. Predict the hybridization and bonding scheme of all the atoms in NClO. So I'm going to put my nitrogen in the middle with an oxygen and a chlorine. There's going to be a double bond there with a lone pair on my nitrogen and 2 lone pairs on my oxygen and lone pairs around my chlorine. So my chlorine here is going to be sp3 hybridized. Forms a single bond. It has 4 electron groups, so it's sp3 hybridized. My nitrogen has 3 electron groups, so it's going to be sp2 hybridized. And so this bond here is going to be direct overlap sigma bond. This is going to be a sigma plus a pi bond. My oxygen is going to also be sp2 hybridized. And there we go.